Algebra 1, hello. Lesson 1, Unit 4, multiplying and factoring polynomial expressions. This unit super duper important for your success in the rest of Algebra 1 and Algebra 2. We need to remember how to factor things quickly and easily to make Algebra 2 easier and to be successful in Algebra 1. So let's go. Write expressions for the areas of the two rectangles in the figures below. If we remember, area of a rectangle equals length times width. Well, if we say one is length and one is width, we can say that the blue one, area equals 2z times z, which is 2z squared. We've got the red one, area is 2z times 8, which is, can't multiply, 16z. Right now, write the expression for the area of this rectangle. If we remember, the area of this rectangle was 2z squared, and the area of this rectangle was 16z. So we can say that the area of both of them together is just 2z squared plus 16z. We added the two rectangles together, therefore we add the areas of the two rectangles together. We could also say that the area would be z plus 8, which is these two added together, times 2z, which if we distribute this sort of backwards, we would have 2z squared plus 16z. What? Those are the same. Crazy. So Jackson has given his friend a challenge. The area of a rectangle in square units is represented by 3a squared plus 3a for some real number a. Find the length and the width of the rectangle. How many possible answers are there for Jackson's challenge to his friend? So we know area equals length times width. And for this particular one, we have 3a squared plus 3a. So we really need to break this into something, that's a question mark, something times something. Okay? So how would we do that? Well, one way I could figure would be to factor the greatest common factor out of these two terms, which looks like it is 3a. And if we factor 3a out, what's left here is just an a, and what's left here is a 1. And I know that's correct because I can distribute this back, and I would get 3a squared plus 3a. So this is one way we could do it, where, for instance, this would be my length. That's written terrible. And this would be my width. Right? So I could say 3a this way and a plus 1 this way. Right? I could do it lots of different ways. I could even just factor out, let's change a color. I could factor out just a 3, and I could be left with a squared plus a, where this would be my length, and that would be my width. I could factor out just an a and be left with 3a plus 3, where that's my length and that's my width, etc. So lots of different ways I could do it. I just need to spread it in, or break that addition problem into two multiplication problems. All right, let's practice. Let's pretend like these are area equations and we want to change them into length times width equations, or we are factoring out the greatest common factor. So if I look here, I have 10a and b and 5a. The factor that's common between both of those terms is a 5 and an a. So if I take a 5a out of here, I'm left with 2b. And if I take a 5a out of here, I'm left with a 1. And I always double check. I know it's correct because if I multiply that back, I get 10ab plus 5a. So I'm looking at these three terms, and I want to figure out the biggest thing common in all three terms. Well, here my number is 3. My letter, it looks like I've got G's. I don't have a G there, so I can't take any G's out. But I have an H, an H, and an H. So I'm going to try to take out a 3H. What's left here is G cubed. What's left here is a 3G squared. And what's left here, I don't even know what's underneath there. There we go. Is a plus 4. And I know it's correct because if I multiply it back, or I distribute it back, I get 3G cubed H minus 9G squared H plus 12H. I get my problem. I double check it back. This is my answer. I'm just double checking. If I look at this one, I have three terms. It looks like I can factor out. Oops, hold on. It looks like I can factor out something from each of the terms. A 6 is too much, but I can take a 3 out of each one of those. So a 3 is definite. I have 2 x's and 3 y's. 1x, so I'm going to take 1x out. 3 y's, 4 y's, 5 y's. So my smallest number is 3. That's what I'm going to take out. If I take all that out of here, I'm left with a 2, 1x and no y's, a 3, no x's, 1 y, and let's see, a 6. Oh, I can't take out an x. See, I caught myself. All right, let me take out the y's. 2 y's left. I have to go back and fix that. So, can't take out that y. That leaves me with x's. That leaves me with 2 x's. I can't take out that x. That leaves me with an x. Okay, let's double check here. Okay, go ahead and distribute it back and make sure we didn't make any other mistakes. 6x squared y cubed, check, plus, let's see, 9x y to the 4th, sweet, plus 18 y to the 5th. Got it. All right, this is in your copies, so let's go ahead and look through it. The language of polynomials. So a prime number is a positive integer greater than 1 whose only positive integer factors are 1 in itself, like 3, 5, 7. They only break into 1 times 3, or 1 times 5, or 1 times 7. 9 is not prime because it breaks into 1 times 9 or 3 times 3. Not prime. A composite number is a positive integer greater than 1 that is not a prime number, like 9. A composite number can be written as the product of positive integers with at least one factor that is not 1 or itself, like 9. For example, the prime number 7 has only 1 and 7 as its factors. Yep, we talked about it. The composite number 6 has factors of 1, 2, 3, and 6. I'll write it like this. 1 times 6, 2 times 3. A non-zero polynomial expression with integer coefficients is said to be prime or irreducible. That's a great word, irreducible. Over the integers if it satisfies two conditions. It is not equivalent to 1 or negative 1. If the polynomial is written as a product of two polynomial factors with each with integer coefficients, then one of the two factors must be 1 or negative 1. Given a polynomial in standard form with integer coefficients, let C be the greatest common factor of all the coefficients. The polynomial is factored completely over the integers when it is written as a product of C and one or more prime polynomial factors, each with integer coefficients. That's what we've been doing, okay? All right, now we're going to multiply two binomials. We have done this with tables a little bit. In Algebra 2, you're going to do it even more, but we're going to practice it. We're just doing binomials. A binomial is two things times two things. Two terms times two terms times two terms. The sum or difference of two terms times the sum or difference of two terms. Okay? Okay. Using a table as an aid. You've seen the geometric area model used in previous examples to demonstrate the multiplication of polynomial expressions for which each expression was known to represent a measurement of length. Without a context such as length, we cannot be certain that a polynomial expression represents a positive quantity. Therefore, an area model is not directly applicable to all polynomial multiplication problems. Because if we don't get a positive answer, you can't have area if it's negative, correct? So we can't be certain that a polynomial expression represents a positive quantity. So this area representation doesn't actually always work, but a table can be used in a similar fashion to identify each partial product as we multiply polynomial expressions. The table serves to remind us of the area model even though it does not represent area. For example, fill in the table to identify the partial products of x plus 2, x minus 5 times each other. Then write the product of that in standard form. So what we would do is multiply x times x and get x squared, x times 5, 5x, 2x, and 10. And then you can sum all of these things up. X squared, this would give us 7x and 10. Standard form means I do my highest terms first. That is a 1 to lowest terms. It's actually sort of like ax squared plus bx plus c is standard form. Always highest to lowest exponents. Okay, so this is the table as an aid, which is sort of like area, even though we don't know if this addition will give us a positive or a negative number, but it's a way to keep things organized. Cool? We can also do the same work without the table. That's why it says without the aid of a table. This method is what we call foiling. Foiling stands for first, outer, inner, last. Let's read this. Regardless of whether or not we make use of a table as an aid, the multiplying of two binomials is an application of the distributive property. Both terms of the first binomial distribute over the second binomial. Try it with x plus y. I'm going to write it again though. Oops. Try it with x plus y times x minus 5. We're going to do it here though. X plus y times x minus 5. We're going to use the FOIL method, which is first, outer, inner, last. If you look like it makes a little face where we have, let's see, an eyebrow, a big smile, and a nose. Okay, looks like a face. You could even say that these are the ears. But we don't have to go that far, right? Goodness, let's see. I'm going to finish this one in red. So I have first, no. First, with his x times x, which is x squared. Outer, which is the outer two numbers, I've got minus 5x. Inner, plus xy. And then last, which is the last two of the binomials, minus 5y. At this point, you would collect any like terms, which there aren't any. So I'm just going to say x squared minus 5x plus xy minus 5y is my answer. FOIL. All right, and let's try example 3, which is called the difference of squares. We use the table method first, which I've got x squared, 2x, negative 2x, and negative 4. If I collect everything on the inside of the table, I get x squared. And then this right here cancels out. Negative 2x and positive 2x are 0. And then negative 4. This is the difference of squares. This means difference. And this is a perfect square. And this is a perfect square. It's a very, very important binomial that's very, very easy to factor. If we did not use a table, I'm going to write it again to use the FOIL method. We have, oops, I see my mistake. No worries. First, outer, inner, and last. You see these two center terms cancel out, and we're left with x squared minus 4 as our answer. Okay, again, I have difference, perfect square, perfect square. Okay, let's try a few. Factor the following. So we're going to change this. When we say factor, I need to change it into two binomials. This is the difference. I've got perfect square and perfect square. I know those are perfect squares because t squared changes into t times t, and 25 changes into 5 times 5. So I'm going to get t, no, let's not write it up there. Sorry. This equals t plus 5 and t minus 5. I know that's correct because if I FOIL them back, I get t squared minus 5t plus 5t minus 25. The center terms cancel out. We're left with t squared minus 25. Here, perfect square, 2x times 2x. 3 times 3 breaks into 2x plus 3, 2x minus 3. I can double check that by FOILing. 4x squared minus 6x plus 6x minus 9. Cancel out. I get 4x squared minus 9. This is my actual answer. I'm just checking my work. Okay, perfect square. I get 4h times 4h. 6k times 6k. 4h plus 6k. 4h minus 6k. These are called the difference of perfect square binomials. They factor into two binomials, which is the plus and minus of the square root of the perfect square. 2 times 2, b times b. So I get 2 plus b, 2 minus b. Every time. Still going. Here I have x squared times x squared and 2 times 2. So I get x squared plus 2, x squared minus 2. But look, this breaks into x times x. Oh no, this does not break into anything. Let's try this one. So right here, this is my answer. I thought I had a second run, but I don't. Here I get x cubed times x cubed and 5 times 5. X cubed plus 5, x cubed minus 5. Alright, so write a general rule for finding the difference of perfect squares. If I write that in factored form, I get a plus b, a minus b. Okay, it's pretty simple, but it's extremely important. I really can't tell you how important it is. Okay? Cool. Okay, let's try a few more. Notice I always go over here and I find the squares. Like this is 3y times 3y. This is 10z times 10z. So I get 3y plus 10z, 3y minus 10z. Here too. A squared times a squared is a to the 4th. b cubed times b cubed is b to the 6th. A squared plus b cubed, a squared minus, that's not a b, b cubed. R squared times r squared, 4s times 4s. That'd be a 4s squared times 4s squared. So let's break this into r squared plus 4s squared, r squared minus 4s squared. Now this one does break into r times r. Let's do this. And 2s times 2s. So I'm going to do that again. The first binomial does not change, but the second binomial actually factors into two more binomials, r plus 2s, r minus 2s. You're going to have something like that in your homework, so just pay attention. Whenever you finish a problem and you have a difference, check that binomial to see if it's factorable again. Okay, the square of a binomial. If I have one binomial and it's squared, I need to multiply the binomial by itself. Common mistake is to take this one and go, oh, it's just x squared plus 9, because you want to distribute that exponent. That's not correct. This is really x plus 3, which you need to FOIL, which they did up there. First times first, outer, inner, last. So we get x squared plus 6x plus 9. Okay, so we would really write this twice, a plus b times a plus b. And we're actually going to come up with a general rule for this once we're done. I get a squared plus ab plus ab plus b squared. A squared plus 2ab plus b squared. I get a minus b first, outer, inner, last. So a squared minus 2ab plus b squared. Okay, try to see a pattern. Another one, a plus 6 times a plus 6. First, outer, inner, last. Gives us a squared plus 12a plus 36. And then I think it's our last one before we come up with our pattern. Write it twice. I get first, outer, inner, last, which simplifies to that. Okay, my pattern is when I have a plus b squared, which I could write a plus b, my pattern is really a squared, 2ab, b squared. If I test that, let's see, grab one of the problems that we just did, a plus 6 squared. Without going through all the steps, I can actually say a squared plus 2 times a times 6 plus 6 squared, which equals a squared plus 12a plus 36, which is what we got on exercise 8. And there we go. Perfect square, squaring a binomial, squaring a binomial. That's the only difference right there when I have plus and minus. Nice work today. Proud of y'all.